All right, folks. Well, welcome back. I hope you folks all had a chance to rest and relax a little bit over the break, and kind of get away from screens and projectors and whatnot, and kind of step away and hopefully get outside for a little bit and kind of enjoy what we have here. But welcome back. And what I would like to do then is I want to try to get done with the discussion of acceleration today and this week if we can. I do want us to meet live, and so I will post for us the Zoom information for the Zoom sessions that we have for our class here. And so I want to just kind of meet live with you folks to see how you guys are doing. Also, kind of give you an update on what we will be doing moving forward. I have been able to, I have been working with a program, with the platform that will allow us to do a little bit of programming. And unfortunately, you won't be able to test it on a real robot and a real build, but it is a simulation build, and it'll allow you to do a little bit of programming. I'm still trying to work out all the issues with that particular app, but the good news is that hopefully we'll be able to get some programming done this semester. Okay, so I will keep you informed about that one. But in the meantime, though, we're going to finish up and continue on with our kinematics work here. There will be a PET lab that I would like you to do, and that will give you a chance to work on and practice kinematics. Here's some hands-on experience. I know that you didn't really quite sign up for this particular type of class here where I'm presenting quite a bit, but with things the way they are, unfortunately, we have to work it out in this manner here, okay? But like I said, I'm going to try my best to get you guys some hands-on work. Folks, you can come by, stick around after lecture today. I will be available through Zoom to take any questions you may have from 1:30 to 2:30 if you have any questions, and see how you guys are doing. Okay, so make sure if there are any questions, make sure you come by and get those, stick around and get those questions answered. Also, keep up with the work, folks. I will post the second. I'll try to get the second the kinematics work sheet extra practice for you. I'll try to get that posted for you today as well. So today on our classroom account, I will post for you the Zoom information for Zoom, and I will try to get up for you the extra practice for the kinematics work here. Okay. All right. So with that said, then let's go ahead and let's pick up where we left off with in class. We were talking about how we can describe motion. Prior to break, we started the discussion of how we can describe motion. We can talk about the direction in which an object moves, how far it moves, and that gives us displacement. Displacement is defined then as the distance that an object moves from the start to the end, okay, from the start to the finish of final position minus the initial position over a given time in a certain direction. Okay, so that's how we define displacement, and thus displacement then is a vector quantity because direction does matter. When we talk about motion, folks, make sure you understand that direction and thus these vector quantities are absolutely important because motion is always in a given direction. Motion is always going to be in a given direction. And so when we describe motion, we have to be able to describe the direction in which the object moves as well. Okay? And so that was displacement. Then we went ahead and we talked about how we could describe how quickly that object undergoes the displacement, which gives us then a ratio that we describe as velocity. Okay, that velocity then is displacement over a given time interval, so it's a displacement over a given time, and the velocity then is also directional, and so therefore velocity then is going to be a vector quantity as well. Okay, the velocity then describes how quickly an object changes its position, okay, how quickly it changes its position. Then what we did, so that was in the first unit, okay? And then what we did is we talked about how then an object, and then we were able to talk about how we could plot the displacement over time, use the graph then to describe velocity as well. Please make sure you review that. That'll be important because we're going to talk about graphing velocity and time and interpreting the velocity time graphs, hopefully today, okay? All right, so with that said then, we talked about how then how we can describe how quickly an object changes its velocity, how quickly it changes its speed and also its direction. So we talked about acceleration as being a change in speed and also a change in direction. I'm going to leave out the discussion of directional change and how that contributes to acceleration until the end of this unit here, but we can talk about how an object can change its speed. And in order to discuss that, then we need to make sure we understand the difference between speed and acceleration. Speed and acceleration can be viewed in the same way. Basically, speed is how fast something is moving, and we can think of velocity in the same way. The key difference then between speed and acceleration, and there's a couple of, there are a couple of key differences between speed and velocity, and that is with velocity, velocity is a vector quantity. It is directional. Speed is a scalar quantity. It is not directional. So we can think of speed then as simply a magnitude, how fast something is moving without considering the direction in which it moves in. With velocity then, we have to consider how fast the object moves, but also the direction that it moves in. So that's the first key difference between velocity and speed. The second difference then is with velocity, we use displacement and how quickly an object undergoes that displacement. Okay, that's velocity. So we only need to take into consideration two positions, okay, the initial position and the final position. So we're taking a look at then how quickly an object undergoes a straight line motion. And that's how you want to think about it. With speed then, the way we calculate for speed then is it's going to be total distance over total time. In that particular calculation then, in that particular instance, we have to take into account the pathway that the object takes in order to reach the end. So with speed, we are considering the total distance over total time. Okay, and so if the object happens to move in a straight line, then speed and velocity will be exactly the same. The magnitude of those two values will be exactly the same. However, if the object does not move in a straight line path, then the speed and the velocity will not be the same. Okay, and so with that said, then when we get to acceleration, okay, we are talking about the change in velocity. Okay, the velocity of an object at some time that's initial and velocity at some time final. And so we're talking about instantaneous velocity. Make sure you remember then, if you need to go back and review the Edpuzzle videos, are still posted there for you. But in one of the videos, we talked about how then that when we talk about velocity at a certain point, we were discussing average velocity, the displacement over a given time interval. However, we can also determine then the speed or the velocity of an object at a single moment in time. We can use limits in order to calculate for that, or we can just go ahead and then we can calculate, we can determine the instantaneous velocity from a position time graph by using a line that is tangent to the curve on that position time graph. And so that's why it's important for you folks to be able to take a position time graph, understand the information that's given to you, interpret it, but also do some basic simple calculations from it. Because remember, we were able to obtain the formula for velocity and speed from that position time graph, because that the slope of the position time graph is the formula for velocity and speed, because it's simply then the change in the velocity, change in the position over change in time. That's the rise over the run. Okay, and so the equation here, and I'm going to introduce to you the equation first for acceleration, then we'll talk about how we can obtain this particular formula from the velocity time graph as well. But if you notice here then with the acceleration, then we are taking into account two velocities: the initial velocity at a given time interval and a final velocity at a final time interval here. So we're taking into account two velocities. These are what we refer to as the instantaneous velocity. That's the velocity at this given time interval, and this velocity represents the velocity at this particular time interval, at this particular time as well. Okay, and so that's how we describe the acceleration. And we're going to see then today, hopefully, that we can obtain this velocity here. Okay, we can obtain this acceleration here by looking at these values on a velocity time graph. Okay, so we can obtain this calculation, this formula from a graph. Okay, and make sure you understand that all the formulas that we use in physics are derived essentially from a graph. Okay, so regardless of how complex or how simple, they are all representations of information that have been placed on a graph. And if you keep that in mind, it helps you quite a bit in understanding where we get those formulas from. Okay, All right, so with that said, then we saw that if we take a look at the dimensional, if we do a quick dimensional analysis here of acceleration, then so acceleration then represents the change in time, the change in velocity over a given time interval. Okay, and therefore then the dimensions then is going to be length over time squared, with the units then being meters per second squared, kilometers per hour squared, but it's going to be length over units of time squared. Okay, all right. Let's go ahead then and let's continue on. Okay. And so with that said, then what we're going to do then when we take a look at acceleration, we need then a velocity at some time initial, okay, and some velocity at some time final. And make sure you understand then that we have to have a reference here. And this, when we reference here, we're going to reference position, a reference position, and a reference time as well. So make sure you keep that in mind. Since this is still one-dimensional motion, make sure you keep in mind then that what we're going to do then is we're going to use either the positive, the x-axis or the y-axis. We have to indicate where 0 is going to be on those axes, the 0 meters, and so that's going to be our reference position. And then the time interval then is going to be based upon some initial time and some final time as well. Okay, so make sure you keep in mind then that we need to have some reference points in order to refer to the velocity, initial and final velocities and initial and final times as well. Okay. All right. And again, we'll be able to work through this as we go through. Okay. Okay. So acceleration then, if it takes into account the velocity vectors, okay, then acceleration itself is also a vector quantity. It is also going to have a position associated with it, and so in a direction. So velocity is also a vector quantity as acceleration. Okay, and so it's going to have direction and it's going to have a magnitude. The sign of the velocity and the sign of the acceleration will be critical for us. And we'll talk about that, what they mean in just a moment, okay? But make sure you remember this. We talked about then the sign, the direction of the displacement has to be exactly the same as the direction of the velocity. And that, I think, is a fairly straightforward, to understand that it's pretty straightforward. The direction of the velocity and the direction of acceleration, the meaning of those two will be important, but it's not going to be as straightforward. And so we will talk about that in just a moment. Okay? And so the direction then will give us then whether the object is speeding up or slowing down. So when we talk about acceleration versus deceleration, I don't really like that term deceleration, because acceleration means a change in velocity. And so you can have either an object that is having a positive acceleration or an object that's having negative acceleration, and understand that positive and negative only simply means direction. Whether it's speeding up or slowing down depends on the direction of velocity as well. You got to compare the signs of both of those. And so that's why it's critical that you include the positive and negative signs in all of your calculations here, because if you do not, then it will be very difficult for you to determine then whether an object is speeding up or slowing down. Okay. All right, so folks, all of this is just kind of review of what we did before break. So we were able then to take that information and use it to solve problems such as this here. Now, when you solve these problems here, folks, make sure you read the problem, identify what you're given, and write that out. Identify what you're solving for, write that out. Write down the formula that you will use that will relate the different values that are given to you in the problem. Rearrange the formula that you need to solve for the unknown, what you're solving for. That's the equation that you will use to solve for the problem, okay, which in the end then you should have the correct units for as well. Okay, so we worked through this problem together. Okay, so real quick then, if we were to follow that technique, okay, we go ahead then, we describe what we were known. Okay, so we were given this value here. Okay, so we're given this value. This is based on the unit. This is a velocity. Okay, and this we said then was our initial velocity. Okay, we are given this time interval here of a 5-second time interval. Okay, we are told then that it stops, and this is going to be important. This is means then that the final velocity is going to be 0. Okay, and so from that then we were able to find then the acceleration for this particular object here rolling up the ramp. We saw then that we had a negative acceleration, and so therefore we take a look, we compare the values here. We had a velocity that's positive. The sign here is positive, so the velocity was positive. Okay, The acceleration when we solve for it is negative, okay? And so when the signs are opposite here, that means then that the object is slowing down. We have an object that is slowing down whenever the signs for the velocity and the sign for the acceleration are in the opposite direction. That means then the object is slowing down. Okay? So make sure you keep that in mind as we move forward with this. Okay. All right. We left off at this particular problem here, and again, look at the video and make sure you review this. But again, we have an object that is slowing down here as well. Why? Because the velocity is positive. When we calculate for the acceleration is going to be negative, and so then the object is slowing down as well. You can kind of, you read this in the problem tells you that it's slowing down, but we know it's slowing down from our sign. So when we, the velocity here, the velocity that was given to us is positive. So the velocity is positive. When we solve for the acceleration was negative. The signs are opposite here, so therefore that's how we know. If it didn't describe for us, that's how we know that this particular hockey player is slowing down. All right, let's go ahead then. And with that said, that kind of takes us to where we, to the new material here. Okay, so we want to be able to examine then acceleration visually as well. And we want to be able to lead up to the discussion of graphs here, okay? But let's go ahead and let's take a look at what we have here, okay? So I have here for you a particle diagram, okay? And then we have the picture here, the picture model and our particle diagram. Remember, a particle diagram basically represents then an object as it moves, okay? What I've included for you here as well then is velocity. So the arrow here represents velocity. The object is moving towards the right along the positive x-axis, so the velocity here is going to be positive. Okay? And again, these signs here are kind of arbitrary. We are indicating then that if the object is moving in a one-dimensional manner along the x-axis here, it's moving horizontally, so it's moving along the x-axis. Convention tells us then that on an x-axis, positive is towards the right, negative is towards the left. Okay? And so therefore then, the direction of motion here is positive. So the velocity here is positive. Okay? Now, if you take a look then at how far the object moves, for each given time interval. So this is the distance that the object moves. Okay, so this the distance that the object moves. You can imagine then that over each time interval, the difference, the displacement here in time interval 1, displacement here in time interval 2, displacement here in time interval 3, and these are all displacements. Okay? And the displacement here, okay, in 4, okay. If I were to tell you then that the time intervals are all equal, T1 is equal to T2 is equal to T3 is equal to T4. If the time intervals are all the same, then the velocities, if you look at the displacements, and just you can measure this out if you want to, if you take a look at the displacements, if the time intervals are all equal, then the velocity for each time interval here will be equal. So therefore, we call this velocity 1, this velocity 2, this velocity 3, this the velocity at 4, okay, and so forth, this velocity 5. All of the velocities will also be equal to one another, meaning then that the velocity doesn't change. That's what this term uniform velocity stands for. Uniform velocity stands for then not zero. Zero velocity is an object that is not moving. So this does not mean then, uniform velocity does not mean that the velocity is equal to 0. Okay? So uniform velocity does not mean 0. Uniform velocity means then the velocity is the same throughout all the time intervals. The instantaneous velocities are all the same. Now, if an object has velocity of 0, does that mean that it has a uniform velocity? Absolutely, okay? Because the object is not changing its velocity. It's sitting in one place. Its velocity is 0, and it maintains that velocity through all the time intervals. The uniform velocity just means then, okay, that that uniform velocity just simply means then velocity does not change. Okay, that's what uniform velocity means. It does not mean that the velocity is 0. Uniform velocity means that the velocity is constant. Okay, so if you want to think about it in that way as well, uniform velocity means that velocity is constant. Okay, All right. So with that said then, if the velocity does not change, let's go ahead and consider this here. If the velocity does not change, okay, so let's go ahead and consider then what happens to the acceleration. Okay? If the velocity does not change, okay, that means then the V final and V initial, regardless of what time interval is it's going to be the same. So therefore, if you subtract the same number from itself, okay, the answer you always get, regardless what it is going to be 0. Okay, over the time interval, whatever the time interval is. And so therefore, if the velocity is constant, if you have uniform velocity, if you notice here from this very simple calculation, we are dividing 0 by time, the acceleration then will also, the acceleration will be 0. Okay, so under conditions of constant velocity, the velocity then, constant velocity does not mean that the velocity is 0, not necessarily mean 0, but it does mean that the acceleration is 0. That means then the object is neither speeding up nor is it slowing down. Neither speeding up, speeding up or slowing down. It's doing neither one of those. It's just maintaining the same speed in the same direction. Okay, so that is essentially what happens when you have then the acceleration and being 0. So whenever the acceleration is 0, the velocity is going to be constant. Okay. All right. So the confusion here, and I just want to wrap things up here. The confusion here then is that if an object is at rest, okay, when an object is at rest, its velocity is 0. So this is an object that is not moving. An object that is not moving, and make sure you understand this, an object that is not moving has uniform acceleration, uniform velocity, and its acceleration is also 0. Okay, so for an object that's not moving, its velocity does not change. Its velocity is constant, and so therefore the acceleration is 0. So for an object that's not moving, its velocity is 0, and its acceleration is also 0. However, if an object is moving, but its speed does not change, it's moving at a constant velocity, it has a velocity at that point, but its acceleration is 0. Okay, and so you want to make sure you keep that in mind as we go through this here, as we go through and we work out these problems here. Make sure you keep that in mind, because tomorrow what we're going to do then is we're going to talk about then what happens when the velocity does change. What is the acceleration going to be? How do we represent that graphically? Okay. How do we represent that using images, pictures, and these particle diagrams here? And so we're going to do this same analysis tomorrow for objects that are not under uniform velocity, that are not under that do not have uniform velocity, which means then its velocity is changing. Okay. All right. So with that said, then I just make sure you watch the video today. There's nothing that you need to turn in for today. Make sure you, when we meet tomorrow, if you have any questions, you ask. Okay? And then I'll post the video for you as well. Okay, so we'll meet tomorrow for a short period of time, and then I'll let you go so you can watch the video for tomorrow. Okay, for tomorrow's lecture. Okay. All right, very good then. So what we'll do is make sure you get the work done, folks. And if you have any questions, make sure you come by and you see. Okay. All right, folks. I will see you tomorrow on Zoom, and I'll take your questions if you have any at that point. All right. Very good.